In this video, we'll start our discussion about some of the applications of aqueous equilibrium by looking at buffers. We'll introduce what they are. We'll look at the common ion effect just for setting up buffers and finding the pH of a buffered solution. So a buffer is something that's going to resist change in pH when a small amount of a strong acid or a strong base is added. So these are extremely important in things like biology to keep your pH regular so that all your enzymes work. So things like your blood and everything are also buffered. These are useful for lab research. So if you're, again, studying a reaction that can occur at a specific pH, you're going to want to regulate changes in this, so you might make a buffer. This is also important for medicine. If you're going to make a drug that is delivered, say, intravenously, and you want to make sure that it interacts at the same pH as your body, again, you'll want to make sure that you buffer that solution. For example, human blood is buffered at a pH of about 7.4. And as I mentioned, enzymes are usually only effective within a small pH range. In another buffered system, if, say, you aren't studying something directly that's a living organism, is something like ocean water. So ocean water near the surface is buffered at a pH between about 8.1 to 8.3, and this is important for things like ecology. Okay, so what's going to be in a buffer solution? It's going to be something that contains a weak acid or weak base and its conjugate. So in other words, a weak acid plus the salt of its conjugate base, so something like HF, and then its conjugate base would be F minus. And so to have that salt would have NaF, or a weak base plus the salt of its conjugate acid. So something like NH3, there's a weak base, and then this would be NH4 plus Cl minus, and this is its conjugate acid. It has to be a conjugate pair for it to work as a buffer. So it can't just be any weak acid plus any weak base. It has to be a weak acid or base plus its conjugate. So let's look at an example of this. So here we have an HF solution with a pH of 1.6. So if we added NaF, its conjugate base, to the solution, what do you think would happen to the pH? Okay, yes, and in this case, the pH would go up. So if we're adding a base to acidic solution, we expect it to get more basic. But with this hint down here, we can also look at this in a little bit more detail. So if we have this HF solution, we have this equilibrium. If we add NaF to the solution, that means we're adding Na plus F minus. So if we're adding F minus to the solution, this will increase. And to go back to the balance, we'd have to push the reaction this way. That would bring the H plus with it. And so we'd lower the overall concentration of H plus in solution and make a more basic solution. Okay, so here is the Ka for HF, that equilibrium that we looked at 25C. What would happen to the equilibrium constant for this if we added NaF at 25 degrees Celsius? So it wouldn't change. Remember, this is an equilibrium constant. The only thing that's going to change it is if we change the temperature. So while we can change the pH, we're not actually changing the constant itself. Okay, so let's look at calculating the pH of a buffered solution. So we have a mixture of the conjugate acid and the conjugate base. When you're working through problems in this section, you always want to start by asking what are the major species in the solution before any reactions are happening. What are the major species if we put HF and NaF in a solution? Right, and this is the answer. So when you're identifying the major species, it's important to keep track of how these things are going to behave in the solution. So remember, HF is at equilibrium, and this Ka is much less than 1. So when we first put this in, we won't actually have any of the H plus in the solution because we are mostly just HF. So again, we're identifying the major species. In other words, if we have any of these equilibriums and Ka is less than 1, we'll only list the reactants of the major species. None of those because we don't have that much in solution before a reaction occurs. NaF is completely soluble, so that's a one-sided arrow. And if this is the case, we'll only write the products. There's none of this left because it dissolves completely. So these are the major species donated from NaF. We also want to keep track, this is an aqueous solution, so water is always going to be major species. It's going to be the most abundant species because we've dissolved it in water. So as a reminder, anything that's weak does not dissolve completely. The products are not going to be major species. So we have our solution and we've identified these major species. And now we can look at some ways to calculate the pH. The first one we'll do is look at making an ice table and finding this pH. Another way that we can do is use the Henderson-Hasselbalch equation. So let's look at this the long way, the way that we've talked about before. So if we have these two species in solution and we want to set up an ice table, first we'd write our reaction and fill in all of our species. So we start with 1.0 molar HF, we don't have any H plus, 0.5 F minus. Since there's a 0 on this side, we know the reaction is going to proceed to products. And at equilibrium, we'd have 1.0 minus X, X, and 0.5 plus X. We can use the small x approximation for this, and we'd want to look up the Ka for HF. So we have the Ka is equal to 7.2 times 10 to the negative fourth, and we have the products over reactants using the small x approximation. That's X, 0.5 plus X is going to be about 0.5. 1.0 minus X is going to be about 1.0. So we end up with X is equal to Ka divided by what was the concentration of the weak base over the concentration of the weak acid, or 7.2 times 10 to the minus fourth divided by 0.5. And that's going to give us 1.44 times 10 to the negative third. This is the concentration of H plus. And so to get the pH, we take the negative log of this concentration of H plus, and this is going to be equal to 2.84. So that's one way to find the buffer pH. There is a much easier way to do this, and this comes a little bit from having used the small x approximation. So since we use the small x approximation here, we get this relationship between the A minus and the AH, and if we want to take the log of everything to begin with, since we know we need to do this to find the pH, we come up with this solution. So the pH is going to be equal to the pKa, this is just the negative log of the Ka, plus the log of A minus over AH. This can only be used for buffer solutions, and this is only going to be the case when the concentration of A minus over AH, so this term right here, is between 10 and 0.1. What this means right here is if this is true, so if the thing in the fraction is between 0.1 and 10, then the small x approximation is going to be a good one, and we can use the Henderson-Hasselbalch. So using it for this particular problem, we can plug the things in much simpler. So the pH is just equal to the pKa, which is the negative log of the Ka, plus the log of the concentration of A minus over the concentration of AH, and that gives us 3.14 minus 0.301, which is equal to 2.84. The same answer we got using an ice table, but much quicker. We could do it all with just one equation if we know the constant. Okay, so let's look at an example of how this resists the change in pH. We are going to now look at what happens if we have a 40 milliliter solution where we have these concentrations. And so we already know its initial pH is going to be 2.84. And what happens if we add 2 milliliters of a strong base to this buffer? So we'll find this pH using a few steps. So the first step, again, is always identifying the major species. In this case, we have our weak acid. We have our salt that dissolves completely to make the weak base plus sodium. And then we've also added the strong base to the solution, the NaOH. So we're going to have OH minus, more Na from the NaOH, and some water. After you identify the major species in these buffer problems, you want to identify what they all are. So here we have a weak acid. This is not going to act as anything. F minus is a weak base. OH minus is a strong base. And water can be both. So once you have the major species, we are always going to react the strongest acid with the strongest base. So in this case, there's our strongest acid. We have two choices for bases, and we have a strong base, so that'll be our strongest base. If we're reacting with a strong acid or a strong base, it's always going to react to completion. By to completion, meaning a one-headed arrow, this is going to be a stoichiometry problem. So we have our weak acid plus our strong base. We're going to get the conjugate base plus water. And we're going to do that until we use up one of those two species. For this, we're going to make another type of table. This will be a before and after table. And we're going to use this before and after table to find the species in the solution after the strong things react. So for the before and after table, since this is a stoichiometry problem, we have to use the moles. Remember, to find the moles for this, it's going to be the concentration times the volume. So for example, for HF, it's a 0.040 liters, because that's 40 milliliters, and the concentration is 1.0 molar, so that's 1.0 moles per liter. And so for HF, we're starting with 0.040 moles. When you do this first step, you can fill in the first line of your before and after table. So again, that's the volume times the concentration for the HF and the F minus. So these are both 40 milliliters, different concentrations. This was 1 molar, this was 0.5 molar. And then the OH minus, 2 milliliters of a 1 molar solution gives us 0.002 moles. Once these are plugged in to the before and after table, we're going to look at the change. Since this is a stoichiometry problem, would identify the limiting reagent. From here we can see this is a 1-to-1 ratio. We have less OH minus. That'll be the limiting reagent. So we'll subtract that from the products, and there's again a 1 in front of these for the stoichiometry, so that's how much reactant we're making. When we put all these together and finish the stoichiometry problem, we end up with 0.038 moles of HF. We've used up all the OH minus. At the end of a before and after table, something should equal 0. Since it's a stoichiometry problem, we should be using up something completely. And then we added that 0.002 moles to the F minus and get this for the final number of moles for the F minus in the solution. Now we can identify the major species in this solution. So now we have HF, still some sodium, F minus, and H2O. So we have the weak acid, nothing, the weak base, and water, which can be both. We no longer have the OH minus because we used it all up in the first reaction. So now in this case we ask, now do we have a buffer solution? And the answer is yes. We have a weak acid and its conjugate base in solution. Since we have a weak acid and its conjugate base, we can use the Henderson-Hasselbalch equation to find the pH. So this is going to be the pH is equal to the pKa plus the log of the concentration of A minus over AH. And at the end of that table, remember we had the moles, so the pKa from before is 3.14. This is the log. To get the moles, we have to divide by the volume, 0.022, divided by the total volume here. Since we added 2 milliliters of base, is going to be 42 milliliters, and then 0.038, and the 42 milliliters. And we'd plug that in to find the answer. You'll notice something that I did here. So first of all, I didn't convert these milliliters to liters like normally I should if I'm trying to find the concentration in molar. However, you'll see that when we set this up, because these are in the same solution, these two values are the same. So while technically we have to use the concentration for the Henderson-Hasselbalch equation, as long as this buffer is in the same beaker, which it has to be a buffer, the volume for the conjugate acid and the conjugate base are going to equal the same. So you can actually plug in moles and concentrations into this equation. So we could have just plugged in the moles that we got at the end of the before and after table as a shortcut to solving this problem. So in this case, this gives us 3.14 minus 0.24, and that's equal to 2.9. So if we added a strong base to this HF solution, we change the pH by 0.06 units. Let's take a look at this in comparison. So there's our buffered solution. We added 2 milliliters of base, and we get a small change in the pH. What about if we had an unbuffered solution at the same pH? So if we had an unbuffered solution, so this would be something like HCl with a pH of 2.84. If we add some base to this, we'll see that the final pH is actually 12.7. This is a huge change compared to the buffered solution. Now the question is, HCl is a strong acid, HF is a weak acid, so why does it change so much more when we add the same amount of base? Well, part of that comes from how we get to this. So remember, to get to this pH here, we had 1.0 molar HF, and we had 0.5 molar F minus. To make a pH of 2.84, from a HCl solution, so remember this is just going to be the concentration of H+. To get here from a strong acid, this would just be the result of the negative log of concentration. So this means that this solution was 1.45 times 10 to the negative third molar HCl. So you'll notice to get the same pH, we needed way less of the strong acid than we did of the acid in the buffered solution. So when we add NaOH, and it's neutralizing these, it's going to react with this first, shift the equilibrium a little bit, but we'll still end up with quite a bit of HF at the end and still have an acidic solution. Whereas in this case, when we add the NaOH, it can react with all the H pluses directly that came from the HCl to get this pH, and there'll be plenty of NaOH left over to give us this final pH that's now a basic solution.